Hi everyone, my name is Jian Song, and I'm from Paris-Saclay University, the Lab of Signals and System L2S, and this is an associated lab with CNRS, Central Supélec, and the University of Paris-Sud in Paris, France. Today I'm going to present a paper entitled On the Feasibility of Interference Alignment in Ultra-Dense Millimeter Wave Cellular Networks, and this paper is submitted to the Asilomar conference in 2016. First of all, I'm going to give you the outline of this paper, which contains 5 sections. The first one is the introduction, which is followed by the system model. We put some key assumptions with the network and the channel models into this section, and then we will do system level performance evaluation, and then after comparing the analytical and the simulation results, the conclusion will be given at the end. Next, let's move to the introduction part, and in this section, I'm going to answer 3 major questions in order to explain the motivation and the objective of this study. So for the first question is why we want to use millimeter wave band. The answer is the use of the millimeter wave frequency band for application to the wireless access to heterogeneous ultra-dense cellular networks. It constitutes a promising solution for achieving the data rate that 5G network is expected to provide. And this figure contains some key techniques and the architecture of the 5G system, and in our studies we only focus on millimeter wave and ultra dense. Then the second question is why we use ultra dense millimeter wave networks. The answer is, in particularly, we studied that millimeter wave cellular networks with an average cell radius of 50 meters and with a transmission bandwidth of the order of gigahertz may outperform conventional cellular systems in dense urban scenarios. The reason of this performance gain is that millimeter wave cellular networks operate close to the noise-limited scenario, while the conventional systems are interference-limited. However, millimeter wave cellular system may operate in interference-limited regime as well, if some practical constraints on the transmission bandwidth and on the antenna beamwidth need to be imposed, and therefore the density of base stations need to be increased in order to provide enough coverage to base stations. Then the system became interference limited. In the above application scenarios, suitable interference management schemes need to be applied in order to exploit the potential millimeter wave networks for wireless access. A promising technique for reducing the other cell interference is interference alignment, since it is capable best using the available degrees of freedom in the interference channels. In IA, interference alignment, cluster of base stations, which serve different mobile terminals on the same physical channel, cooperate and apply linear precoding methods to suppress the other cell interference at each intended mobile terminal. If applied to interference-limited millimeter wave cellular networks, interference alignment provides opportunities for suppressing the strongest interference and enhancing the coverage and rate. The larger the number of cooperating base stations is, in general, the smaller the other cell interference is, and therefore, the better the performance is. In order to appropriately work, however, interference necessitates channel state information at the base stations. This is usually obtained with the aid of the pilot signals that are transmitted before the data signals. In general, the larger the number of cooperating base stations is, the longer the time for estimating the channel is. This negatively affects the achievable rate of IA interference alignment. This is the answer of the third question. So, motivated by the above considerations, we investigate the potential throughput of IA for application to millimeter wave cellular networks. The objective is to quantify the interference reduction versus training overhead trade-off of IA as a function of the number of base stations with a mathematical tool called stochastic geometry. The next chapter, we are going to introduce the system model, which contains 6 sections. The first section is a cellular network model, which is based on the Poisson point process (PPP). Okay, we consider a downlink cellular network where the base stations are modeled as points of homogeneous PPP with density lambda bs. Also, the mobile terminals are modeled as another independent homogeneous PPP with density lambda mt. Each base station and mobile terminal are equipped with NT transmit and NR receive antennas respectively, and we assume the saturated traffic conditions, which means the base stations are all active. And then each base station is assumed to emit a constant transmit power P. And this figure is generated by MATLAB, which denotes the general PPP-based cellular network model. In this figure, all the base stations are uniformly distributed in the given area, and the number of base stations obey Poisson distribution. And next, I'm going to explain the channel modeling, which contains blockage modeling and path loss modeling, shadowing modeling, and the fast fading. First of all, as for the link state model or blockage model, this is behind the theory called multi-ball. And the idea, based on the multi-ball approximation, lies in replacing the actual loss and loss probability of a typical mobile terminal with an approximated function, which still depends on the base station to mobile terminal distance r, but is a piecewise constant as a function of r. In particularly, we split the base station to mobile terminal distance in b+1 regions, which corresponding to b balls whose center is at the mobile terminal. Let the radius of b balls be d1 less than d2 less than d3 and less than up to db. Then we will formulate the link state model as a function in these slides. And then later, we will apply this to formulate the path loss intensity measure, which is a main ingredient of stochastic geometry. Also, we consider the path loss based on a power decaying function, which leads to the tractable mathematical expression. Here, k denotes the path loss constant, and beta denotes the path loss slope. As for shadowing, we consider that it is distributed according to a log normal random variable with mean mu and standard deviation sigma. And we will have the PDF function in these slides. In addition to blockage, path loss, and shadowing, each base station to mobile terminal link is subject to fast fading, which is modeled as an independent complex channel gate denoted by H. Then the power gate H square is assumed to follow an exponential distribution with mean value sigma loss equals to sigma n loss equals to 1. Okay, in our channel model, we consider all the factors which may affect the performance of millimeter wave cellular networks. Now we also take into account the directional antennas for enhancing the link reliability and reducing the other-cell interference introduced from high-frequency band. We assume that the directional beamforming is applied at both the base stations and mobile terminals, and a two-lobe model for radiation patterns of the directional antenna is assumed, which is formulated on the top of the slides. And the typical mobile terminal and its serving base station are assumed to estimate the angles of arrival and to adjust their steering directions so that the directivity gain of the intended link can be the multiplication of the main lobe gain of base station and the main lobe gain of mobile terminal. The directivity gain of the interfering base stations, GI, are assumed to be randomly oriented with respect to each other and to be independently and uniformly distributed from -pi to pi. Therefore, we will have the PDF of GI in these slides as well. And all the above sections that we mentioned are the main component to compute the received power and SNR. And at this stage, it is necessary to introduce the access technique that we applied, or it can be called cell association criterion. In this paper, the cell association is based on the highest average received power criterion, which accounts for the pass loss and shadowing, while the fast fading is ignored. We assume that the loss or in-loss status of a base station to mobile terminal link is independent of the loss or in-loss status of any other links, and also no spatial correlation among the base station to mobile terminal links is considered. And in the chapter of the system model, we also add two more sections as supplementary materials to explain the tractable mathematical modeling and the story behind interference alignment. As for the first section, the tractable mathematical modeling, it is based on the theory called the intensity measuring approach. And generally speaking, the intensity measuring approach is an approximation that allows us to account for the impact of blockage and shadowing at an affordable analytical complexity. With aid of the intensity measuring approach, the set of the generalized pass loss corresponding to the PPP of base stations can be shown to be an inhomogeneous PPP, whose intensity measure is a summation of that of loss and unloss component. For a specific link state S, it can be formulated as a function which is shown in the bottom of this slide, intensity measure. And then we move to the last section of the system model. And as mentioned before, the ultra-dense millimeter wave cellular networks may be interference limited. Therefore, allowing the cooperation among base stations may reduce the impact of strong interference. As an example, base station cooperation for interference reduction, we focus on the interference alignment. First, the K base stations providing the smallest K generalized pass losses to the typical mobile terminals are identified. We have the smallest generalized pass loss, and we also have K's smallest pass loss for K equals to more than 1, which is 2, 3, and up to K minus 1. Then the K cooperating base stations apply linear precoding and decoding vectors in order to suppress the other cell interference generated by K-1 interference base stations for the typical mobile terminal. And now we assume we are going to use the mean leakage algorithm to obtain the interference alignment. And the base station outside the cluster of K cooperating base stations still create other cell interference towards the typical mobile terminal. And now it is worth noting that the number of cooperating base station K needs to be chosen according to the feasibility conditions, which is NT plus NR greater and equal to K plus 1. And the minimum number of transmitter antenna and receiver antenna should be greater than 2. And in order to compute the pre-coding and decoding vectors, the cooperating base stations need channel state information of the link inside the cluster. To obtain estimates of base station to mobile terminal channel gains inside the cluster of K cooperating base stations, we use the pilot overhead model and with the frequency division duplex systems (FDD). Simply speaking, a block fading channel model is assumed, with the block length expressed in terms of multiple of the symbol time NB, which is a component dependent on the Doppler spread, and then based on the pilot overhead model, the number of pilot symbols NP, which is the summation of NPF and NPR, NFB, and NPD. Those pilot symbols are defined based on the 3 parameters, which are the cluster size K, the number of transmit antennas, and the number of receive antennas. Now in this paper, we assume NPF equals to KNT, NPR equals to KNR, and NFB equals to K squared multiplied by NT, and NPD equals to K. Those symbols denote the 4th stage based on the pilot training sequence. Here we define tau equal to MB minus MP over MB, which accounts for the effective resource used for data transmission. And by using this, we can formulate the signal to interference plus noise ratio (SNR). And after the system model, I'm going to explain the system level performance evaluation, which contains all the formulated mathematical frameworks. First of all, the SNR can be expressed as the first equation on this slide, which contains the intended signal and intra-cluster interference and inter-cluster interference. Due to the interference alignment technique and the pilot overhead training for CSI, we only have the fading estimate for the intended signal, while the corresponding estimate error can be treated as the interference in the denominator of this equation. Also, for the intra-cluster interference, we only have the estimation error because the channel estimate of the power gain estimation is reduced due to the interference alignment. However, you will find both the channel estimate and the corresponding error exist in the intercluster interference. Note that here, all the estimate channel fading gain and the estimation error are exponentially distributed random variable, and they can be computed based on the last equation of this slide. Therefore, we can finally express the potential throughput PT as twofold integral of x and y, where x denotes the smallest path loss and y denotes the case smallest path loss, and their joint PDF is given by FL of x and y in this slide, which is fully described by the path loss intensity measure. Also, in this general mathematical framework, or PT, we express the components of intracluster and intercluster interference as the form of moment-generating function, and here we express theta s to reflect the impact of antenna directional beamforming, and we also express upsilon s to reflect the impact of blockage model based on the multi-ball in order to represent the realistic blockage. Here we use random shape model. And next, we move to the chapter of numerical and simulation results. Here we select the parameters of path loss and shadowing, which correspond to 28 GHz carrier frequency. And as for the two-lobe antenna model, we have the main lobe gain equals to 20 dB, and side lobe gain equals to minus 10 dB, and the beam width of the main lobe equals to 30 degrees. And in order to satisfy the feasibility condition of interference alignment, we choose NT equals to 64 and NR equals to 2. Also, here we select the optimal decoding threshold, which is 30 dB. And as for the realistic blockage model, here we apply the random shape, where A equals to 1 and B equal to 0.046. Here, for the simply speaking, we ignore A in the equation. After intensity matching, we got the parameters for three-ball blockage model to obtain the better approximation. And based on those parameters and setup, we can validate the proposed framework of PT against the Monte Carlo simulation. And in Figure 1, we illustrate the PT as a function of the density of base stations and of the number of cooperating base stations. We observed that the proposed mathematical framework is in good agreement with Monte Carlo simulations. And due to the presence of blockages, an optimal deployment density for the base station exists. It depends on the number of cooperating base stations K, or cluster size K. As far as the impact of IA is concerned, a too large cluster size will lead to a considerable reduction of the PT because of the associated training overhead for channel estimation. An optimum value of K that maximizes the PT. And in Figure 2, we provide the maximum PT with respect to the density of base stations as a function of K. And we can conclude that in the above setup, and K equals to 7 corresponds to the optimal number of cooperating base stations, which optimally trade off the interference reduction and channel state overhead. The maximum gain originating from interference alignment is of the order of 0.7 bits per second per hertz from this figure. So in conclusion, we have proposed a tractable mathematical framework for estimating the potential throughput of millimeter wave cellular networks with interference alignment. And our study demonstrates that due to the training overhead for channel estimation, an optimal number of cooperating base stations exists, and due to the presence of blockages, an optimal density of base station exists. And our proposed mathematical framework is in good agreement with simulations and provides a tractable tool for optimizing millimeter wave cellular networks. And more details can be found on the reference list. Okay, so thank you for your attention.